Swayam Prabha. Digital India. Educated India.
Good morning, welcome to today's class. We are continuing in our series covering basic mathematical tools. Today's first topic is concepts from multivariate calculus. This is the calculus in finite dimensional vector space. The keyword is multivariate. First, I'm going to start by defining functions. A function consists of three objects. One, A, the domain, B, the range, and F is an association between points in A to points in B. A is a set, B is a set. A could be a finite set, B could be a finite set, or A could be infinite and B could be infinite. So there's quite a variety of choices. So given a domain and a range, there are several ways in which we can associate points in the domain to points in the range. But there are few conditions for something to be called a function. For f to be a function from A to B, f has to assign values to every member of the domain. That means it cannot leave any member unspecified, the value of the function for any member unspecified. And also by definition it's single value. What is the difference between a single valued function and a multivariate function? In a multivariate function, x can have more than one image. In a single valued function, every x has to have a unique y associated with it. So look at the picture now. A is the domain, B is the range, x is a point in A, y is associated with x by the function. This association has to be specified for every point in f, and this association has to be such that for every x there is a unique y. So these are the two basic restrictions. All the members of the domain must be covered and it must be single value. That is a function, that's a class of function we are going to be dealing with. F of x is called the value of the function. Y is equal to f of x is called the image of x. And f of x is unique for every x belonging to A. So pictorially, I can think of function as a box, black box. X belonging to A is an input. F of x belonging to B is an output. So a function transforms an input into an output. Now we are going to talk about special classes of functions. F is said to be injective or one-to-one. If I picked any 2 points x and y not equal, the values f of x is not equal to f of y. That means distinct points in the domain are mapped onto distinct points on the range. For this to be defined this way, the number of members of A must be less than or equal to the number of members of B. And that makes sense. Why? If A has n members, and if each of the x is going to be associated with a y, and two distinct x's have to be mapped to two distinct y's, B must have at least as many number of points as A. And in here, A is called the set, this is called the cardinality of the set, cardinality. And it represents the number of members of A is equal to the number of members of A. Members of A. So the cardinality of A cannot be larger than the cardinality of B for function f to be injective or one-to-one. F is said to be surjective. Means what? The entire set B can be covered by picking different points in A. So it is a set of all f of x such that x belongs to A. That means A can have more number of points than B, so the cardinality of A is greater than or equal to cardinality of B. Now I am going to combine the two. F is one-to-one and on-to. So it is called bijective. F is said to be bijective if it is both injective and surjective. Injective means what? Distinct points mapped to distinct points. Surjective means what? Every point in the range has an associated point in the domain. The entire range set is covered by the function using points in A. So what are the examples of functions? Absolute value function, x square function, sin x, e to the x. These are some of the standard functions. I would like to leave it as an exercise to check whether these functions are injective, surjective, or bijective. That's an important exercise. I would like to ask you to perform that, work that problem out. Now we are going to go for another types of function, another classification of functions. F is a scalar valued function of a scalar. So what does it mean? I have a box F. The input is x, the output is f of x. The output belongs to R, the input also belongs to R. So output is a scalar, input is a scalar. F is called the scalar valued function of a scalar. What are the examples of such functions? F of x is equal to x log x. F of x is equal to 2 to the x. F of x is equal to e to the x. These are scalar valued functions. X is a scalar, e to the power of x is a scalar. The second class of functions are called scalar valued function of a vector. Here, the n should be here. In the case of scalar valued function of a vector, here is f, here is x, that belongs to Rn, and f of x belongs to R. It takes a vector and puts out a scalar. That's called the scalar valued function of a vector. Sometimes this is also called functional, cost functional in optimization. So most of the optimization technique, optimization is done over a multivariate space of n dimension. The cost function is defined over this multivariate space, and that's a scalar. So what are the examples of such functionals or a scalar valued function of a vector? The norm of x, x transpose x, this should be x transpose ax. Also, if I fix A to Rn, f of x is the inner product of A with x. Here A is fixed, it's a function of x, and it's a linear function. The norm is a nonlinear function. These are examples of scalar valued function of a vector. The third one is called the vector valued function of a vector. This must be Rn, this must be Rm. Sorry for the, here is an f. I'm going to give an input Rn. The output f of x is Rm. So the function takes a vector as an input, it puts out a vector as an output. That's called the vector valued function of a vector. So in this case, I'm going to define my output to be f subscript 1, f subscript 2, f subscript m. There are m outputs coming out of that, and that's a vector. So let's work an example. Let n be equal to 3, m be equal to 2. That means x has 3 components, x1, x2, x3. f of x has two components, which is f1 of x, f2 of x. f1 of x is x1 square plus x2 square plus x3 square. f2 of x is x1, x2, x3. So in this case, I have a vector valued function of a vector. In the case of multi-objective optimization, we need vector valued function of a vector. For example, in the design of a car, I want the car to be cheap. I want the car to be safe. I want the car to be looking good. I want the car to be giving more mileage per liter of petrol. So there are multiple criteria that I would like to be able to express. So f1 could be one criteria, f2 could be another criteria, fm could be another criteria. So in the multi-objective optimization, we have to deal with vector valued function of a vector. In the uni-objective optimization, there is only one objective, one cost function. We have to deal with scalar valued function of a scalar. Then there is another set. Given an interval AB in the real line, so AB, 2 points in the real line, given the interval AB, I can define continuous functions over this interval. So CAB refers to the set of all continuous functions over the interval a comma b. Now, a function can be discontinuous, it can be continuous, it can be continuously differentiable to the order 1, order 2, order k. So if I say CKAB, it is a set of all functions with continuous derivatives of order up to k. So CAB refers to set of all continuous functions. Set of all continuous functions need not be differentiable. So C1AB means set of all continuous functions differentiable once, where the derivatives are continuous as well. So CK is a set of all continuous functions with continuous derivatives of order up to k. So we will have a reason to consider many different types of functions. So this is the short list of functions of interest in many aspects of data science. Now I'm going to come to the very fundamental concept of the gradient. So we are going to be concerned with the scalar valued function of a vector. So that means, how do I say the scalar valued function of the vector? F is defined from Rn to R. Rn is the domain, R is the range. So it takes vectors as input and outputs a scalar. So if I took 2 points x and z in Rn, let's consider 2 points x and z in Rn. We say f of x is differentiable. I'm talking about the n-dimensional space now. If and only if there exists a vector u such that f of x plus z plus f of x. So let's look at this now. Here's a point x, here is a point x plus z. Z is a very small quantity, small vector compared to the magnitudes we are concerned with. So the difference between the two can be very well approximated by the inner product of u times z. Z is the z that is given here. Z, z, they are the same. But the rest of the terms are all higher order terms in z. Z is small, so higher order terms mean z square, z cube, and so on and so forth. That's called the higher order terms. And what is the property of the higher order terms? HOT is z divided by the norm of z. As the norm of z goes to 0, all the higher order terms tend to 0 in the limit. So as z goes to 0, x plus z move towards x. As x plus z move towards x, I can express the difference between the value of the function at the point and at the point, the difference between the two, as simply an inner product of u times z. And what is that u? U is a vector defined as the gradient of f of x. So this is the very general definition. So this is the general definition of a gradient. But practically, how do I compute gradient? Gradient is a vector. It is denoted by this symbol. It is a vector of partial derivatives. Partial of f with respect to x1, partial of f with respect to x2, partial of f with respect to xi transpose. So that's the vector of partial derivatives of f at the point x is called the gradient of x, or gradient of f at x. So what are the properties of the gradient? So del is called the gradient operator. In the univariate case, this is the analog of d by dx. So I'm now going to talk about many of the standard properties of the gradient operator del. So let f and g be two functions from R into R. The gradient of the sum is the sum of the gradients. So that is additive property. If I multiply a function by a constant c, the gradient of Cf is equal to c times the gradient of f. That means the homogeneity property. If I multiply two functions f and g, if I talk about the gradient of the product, you all know the product rule in the differential calculus. So this is the analog of the product rule. So f of x times the gradient of g plus the gradient of f times g. That's the product rule. So additivity property, homogeneity property, and the product rule property. Now I'm going to define what's called the directional derivative of f at the point x in the direction z. That means I have a domain, I have a point x, now I'm fixing a direction z. Now what is it I want to ask myself the question? How the function changes, what is the rate of change of this function along the direction? Okay? So that's what's called the directional derivative. I'm sure you must have been introduced to that. So the directional derivative in the direction z is defined by f prime of x comma z. It depends on f, it depends on x, it depends on z. I'm going to denote it f prime x comma z. And what is that? It's the inner product of the gradient of f at the point x with the vector z. And what is that? This is the product of the norm of f of x, norm of z times cosine theta. That's the inner product formula we already know. We already know. So the notion of a, so what is that we have introduced now? The notion of a gradient, the notion of a directional derivative. A differentiable function. Okay, now here is one of the fundamental properties. Any differential function changes at a maximum rate in the direction of the gradient. That's a basic fact. Let's look at this now. Why? So at f of x, if this is the gradient, if this is z, the directional derivative of this is the gradient along this direction. So let this be the angle theta. The directional derivative is given by the inner product of the two. Cosine, when is it maximum? When theta is 0. So when z is equal to gradient of f of x, what is the inner product? Inner product is the inner product of f of x times z is equal to inner product of del f times del f, and that's equal to del f whole square. We all know using the normal condition, and that's the maximum. So what does this tell you? This essentially tells you a function changes at the maximum rate along the direction of the gradient. This is one of the fundamental rules, and this is the rule that is used in design of the minimization, maximization algorithm in optimization theory. The gradient algorithm tries to seek the minimum by moving along the gradient. Why? This is the reason. Why? This is the reason. That means a differentiable function changes at the maximum rate along the direction gradient, and this is the result of the Cauchy-Schwarz inequality. This is the result of the Cauchy-Schwarz inequality. Now I'm going to consider a function of a function. So let t be the time variable. X of t is a function of time. X of t is a vector. X1 of t, x2 of t, xn of t is a vector. So I have a vector, each of whose components changes as a function of time. So I can now consider a function. Let me erase this. I can consider a function f of x of t. I want to be able to compute the total derivative of f. What is the total derivative of f? It is the derivative, partial derivative of f with respect to x1 times the rate of change of x1 with respect to t. Likewise for x2, likewise for xn, likewise for xn. So this is called the total derivative with respect to t, and that follows with the chain rule. These are extensions of the rule that we have learnt in ordinary differential calculus, which is the univariate calculus, to multivariate calculus. Now comes the next definition. And again, F be Rn to R. I'm going to define a Hessian matrix. In the case of univariate calculus, I have df by dx. I have d square f by dx square, first derivative, second derivative. The equivalent of the first derivative is gradient. The equivalent of the second derivative is called Hessian. So del square f, in this case, is going to be a n by n matrix. So the second order partial derivative matrix. And we all know, and by definition, this is the matrix. The diagonals are the second derivative of f with respect to x1, x2, x3. The off-diagonal elements are mixed derivatives. And we all also know from basic calculus, if f is continuous, del square f of del of xi del xj is equal to del square f by del xj del xi. The mixed partial derivatives are symmetric. Therefore, this is the n by n matrix. It is a symmetric matrix. This symmetric matrix is called the Hessian. You don't have to say Hessian matrix. Hessian, by the definition, is the second order matrix of partial derivatives of f. You can stop me whenever you think you have a question. Please do. Now I'm going to, so far I was dealing with functions which are scalar valued function of a vector. The output is a scalar. Now I'm going to go to vector valued function of a vector. What is that? The f defines the points from n to m. We already seen that today morning. So x is Rn, f of x is f1, f2, fm. Each one of these f's are functions. Now I'm going to talk about the Jacobian. That's an important matrix associated with it. Now, you please recall the derivative of f1 is equal to the partial of f1 with respect to x1, partial of f1 with respect to x2, and partial of f1 with respect to xn. Derivative is generally column vector, but look at this, the first row. It is the transpose of the derivative of f1, the gradient of f1, transpose of the gradient of f2, transpose of the gradient of fn. So this matrix is a m by n matrix. So there are m rows and n columns is R m by n. This matrix is called Jacobian matrix. So where do Jacobian matrix come into play? When you are having vector valued function of a vector. So notice that the rows of dx are the transpose of the gradient of f of I is equal to 1 to n. Now I'm going to give you some quick examples. Let a and x be vectors. Let f of x be equal to A transpose x, and that can be defined as summation xi ai. So what is the gradient of that? The partial of f with respect to x1, x2, xn. The partial of this with respect to x1 is a1, with respect to x2 is a2, xn is an, and what is that is a. So I got the first formula for the multivariate calculus. If f of x is A transpose x, its gradient is A. It's like in differential calculus we learned d by dx of sine x is cosine x, d by dx of e to the power of x, e to the x. We have a table of derivatives. So this is the first entry in the table of gradient in multivariate calculus or multivariate analysis. Everybody? Okay. Now, I'm going to take a symmetric matrix, A, B, B, C. I'm also symmetric, and let me also assume it is positive definite with the loss of generality. So f of x is x transpose ax. If I multiply x transpose ax, I get this ax1 square plus 2b x1 x2 plus c x2 square. I want you to be able to do and then verify all these things. Now, if I compute the partial derivatives of this with respect to x1, that is equal to 2ax1 plus 2bx2. If I compute the partial derivative with respect to x2 is 2bx1 plus 2cx2. This can be rewritten beautifully as 2 times abbc x1 x2 2ax. That means if f of x is equal to x transpose ax, its gradient is 2ax. If f of x is equal to A transpose x, its gradient is A. Okay? Now I can combine the two. Let f of x be equal to 1/2 of x transpose x minus b transpose x. Oftentimes in optimization theory, this will be the structure of the cost function, quadratic function. So what is the gradient of that? The gradient of this is, look at this, the gradient of x transpose ax is 2ax. 2 1/2 will cancel. So the ax and the x, this is b. So gradient of the gradient of this function is ax minus b. So if I want to find the minimum, I do know the minimum occurs at where the gradient vanishes. You all know that. Now I'm going to give you further examples of computing gradient of various kinds of functions. So let h of x be a m-dimensional function. So x is here, please understand, x is a vector. H is also a vector. H is the m vector, x is the n vector. Now, I'm going to define a new function, f of x is equal to a transpose h of x. That's equal to h transpose a of x, h transpose x of a, where a is a m vector, x is Rn. Now do you understand that this is a, f of x is a function of a function? Everybody please. So what is the gradient of this f of x? The gradient of this f of x is equal to the transpose of the Jacobian of h times a. You remember Jacobian we talked about? The transpose of the Jacobian of h times a. The Jacobian is a m by n matrix. So this is a formula that will come very useful when you do multivariate optimization. And I believe you all do multivariate optimization. Now let's consider, so what is this? F of x is a linear function of h. Now I'm considering the same h. I'm going to give a f of x is equal to a quadratic function, h transpose a h of x. What is the gradient of that? The gradient of this is 2 times the transpose of the Jacobian of h times ax. Okay? These are all formulas. I would want each of you to be able to verify this. In my course, when I teach, these are all homework problems. You cannot derive all the things in the class, so you do the basic things and you need to be able to derive very fast. So, the next one is composition of functions. Suppose f is a function from Rm to Rn and g is a function from Rn to Rd. With me? Then I am going to define a function x from Rm to Rd. So h is a combination of f and g. So to compute h, I first apply f and then followed by applying g. Everybody with me please? So h of x is equal to g of f of x, which is denoted by g, a circle of f of x. So this is called the composite function. Composition of functions. With me? E to the power of sine x is a composition, right? X to sine x and then e to the power of sine x. Same thing in here. So what is the Jacobian of this? The Jacobian of this is the product of the Jacobian of g followed by the product of the Jacobian of f. Jacobian is a matrix. Matrix multiplication is not commutative. So you have to be truthful to the order of multiplications. I hope you are all with me. So these are all very good exercises. My suggestion is if you want to excel in optimization theory, if you want to excel in multivariate optimization, these are the nuts and bolts that you need to be thorough with in order to be able to do your problem. So when you are doing optimization, you cannot have difficulty in differentiation. Are you there? That's too late. That's too late. So how do you equip yourself with all the fundamental tools that are needed in optimization? And that's what I'm covering here. Now I'm going to go to the important concept of what's called the Taylor series. So what is the idea of Taylor series? I have a domain, I have a point x, I have a point x plus z, and z is small. X is a vector, z is a vector. I'm sorry, I'm first talking about Taylor series expansion of a scalar valued function of a scalar, simple case that we normally do in basic calculus. So x is a number, z is a small number, x plus z is another number, I want to be able to compute the value of f at x plus z. Knowing x and z and the value of f, how can I approximate or compute the value of f? The Taylor series expansion essentially tells you f of x plus z is f of x plus the derivative of f with respect to z, 1/2 of the second derivative of the z square, and 1 over factorial k, the kth derivative times z to the power of k. I'm sure you all must have done. If you have done BE or a bachelor's course in mathematics, you should have been introduced to Taylor series. So this is the Taylor series in single variables. In principle, this is an infinite series. So but I cannot, in practice, I cannot deal anything infinite. I have to truncate it. So here I have truncated at the kth degree. So this is what's called kth order approximation of the value of the function f of z, f of x plus z at x, where z is called the perturbation. I am trying to estimate the value of the function at a neighborhood point given the value of the function at this and all of its derivative at x. I am assuming I know the first derivative, second derivative, kth derivative. I also know the value of the function. So if I know the value of the function, all the k derivatives, then I can approximate the value of the function in a small neighborhood around the x. Now I am going to consider the Taylor series expansion for the vector valued, scalar valued function of a vector. Scalar valued function of a scalar to scalar valued function of a vector. So in this case, I am only giving you a second order Taylor series expansion. And how does it come? F of x plus z is equal to f of x plus the inner product of the gradient of f with respect to z. X is a vector, z is a vector. Please remember that. They are in the point in the domain. And what is this? This is a Hessian. So what is this term corresponding to? This term corresponding to d square f by dx square times, d square f times z square, if you go back to that. So this is the term. The analog of that term in multivariate calculus becomes a quadratic function, z transpose Hessian times z. Now you also know that the Jacobian matrix is essentially consists of the transpose of the gradient. Therefore, I can rewrite this term to be the Jacobian. Therefore, the second order Taylor series expansion for a scalar valued function of the vector is f of x plus z is equal to f of x plus Jacobian times z. The Jacobian is a matrix, please remember that, and the quadratic function. So this is the Taylor series expansion for scalar valued function of a scalar. This is the expansion, Taylor series expansion second order for scalar valued function of a vector. Now I am going to consider Taylor series for vector valued function of a vector. What does it mean? X is a vector, z is a vector, f itself is a vector. So f of x plus z is equal to f of x, the Jacobian of f times z plus a second order term. The second order term is a much more complex term. Please remember, f is a vector, f of x is a vector, this is a matrix times a vector, so this must be a vector. So this is Jacobian, I already talked about that. So now I am going to define what this term is all about. This is a vector which has m components. The first component is z transpose the Hessian of f1 times z, z transpose Hessian of f2 times z, z transpose Hessian of f1 times z. With me? So what is that I am trying to do? I am trying to stack the scalar valued function Taylor series one by one and collect them as a vector, and that's the vector. That's a vector. And what are these terms? These are Hessians. So these are the Hessians. So Hessian Jacobian, first derivative, second derivative. With me? So first derivative, its analog is gradient or Jacobian. Second derivative, Hessian, and this is a vector of a vector of quadratic forms with respect to Hessians. These are very basic things. Generally, you don't do these things in calculus class, but this is what is needed when you want to do mathematically analysis in multivariate case. Now I'm going to talk about an associated concept called variation, first variation and second variation. I'm going to be talking about with respect to scalar valued function of a vector. So I'm considering a point x. I'm trying to perturb the component x1, x2, xn. Let delta x1, delta x2, delta xn be the small perturbations. Perturbation means what? I'm going to add. So let delta x be a small vector which is being added to x. Now I'm going to do a different notation now. Delta f is the change in f. Change in f. Delta f is the gradient of f. You remember that? That's the difference. So delta x is the resulting change in f of x induced by the increment in f of x. So what is that? F of x plus delta x. So earlier I called this delta x as z, right? Here I'm relabeling z to be delta x. You believe delta x, when I say delta x is small, you didn't believe probably from his question I can z means it is not small. Z is small, okay? So we set what it is. The symbol z, they're small, here delta x is small. So if I apply that Taylor series expansion for this function, a second order Taylor series, you already know this is equal to f of x plus the gradient times that plus this. Everybody? Now what am I going to call? I'm going to call this. I'm going to call this. This is called the first variation in f. This is called the second variation in f. Are you with me? First variation in f is induced by the gradient. The second variation in f is induced by the Hessian. So I want to be able to compute what is the contribution by the gradient to the change in the value of the function. What is the contribution of the Hessian to the change in value of the function? With me? So this function, this quantity del f, I have expressed this as the inner product of gradient times delta x. By definition, that's called the first variation in f of x. So what is first variation? It is simply the directional derivative in the direction delta x. You remember the directional derivative I have already introduced. So it is the magnitude of the directional derivative of f along the direction delta x, and that is given by the inner product. What is the second variation? The second variation is given by the quadratic form, the value of the quadratic form given by delta x transpose Hessian times delta x. Therefore, if I perturb a function by a small quantity, if I want to be able to calculate the exact change is related to first variation, second variation. So I'm trying to decompose the total change in f. Its contribution by first derivative is contribution by second derivative, its contribution from third derivative, and so on and so forth. This ability to associate the total change to different components is an important part of understanding how the value of the function changes in small neighborhoods. With me? And that's what's called variation. I'm sure you all have heard the notion of what's called variational calculus. With me? So this is called the notion of first variation, second variation. So what is the first variation? When you go from scalar valued to vector valued function? F is a vector valued function. X is Rn. Delta x is a perturbation of x. I want to be able to compute the first variation delta f. Everybody with me, please. So first variation f1 is given by the inner product of gradient of f1 with delta x. First variation of f2 is given by that. First variation of f1 is given by that. So in this case, it's a vector valued function, right? So the change in function, the first variation itself is a vector whose components are given by this. Now, delta x is a common factor. I can compute all these things, and that becomes Jacobian. Therefore, the first variation of a vector valued function of a vector is related to the Jacobian times the perturbation. Jacobian times the perturbation. Examples. Let f of x is equal to A transpose x. Then the gradient of f is A. We have already seen that. Therefore, delta f is simply delta x times A. This is x transpose Ax. So f of x is equal to 1 half of x transpose Ax. Delta f is equal to, the gradient of this is Ax. So this is inner product of Ax over delta x. A is symmetric. If I have a quadratic function, z minus hx transpose z minus h of x, as f of x, its variation is given by this. Now I am going to give you a collection of exercises. I don't want to read them. Please understand, you become a good cook by cooking repeatedly. You become a good musician by singing continuously. You become a good cricketer by playing cricket for a long time. You become a good mathematician by working lots of problems. Are you all with me? So these are exercises. I would like to be able to work on this. That finishes our exposure to multivariate calculus. A very good book. Is a book by Apostle, 1957. It's a classic book. It's one of the very good books. I'm sure your library has it.